I would like to share with you some of our work on water harvesting from air. And I would also like to say that we would like to do this anywhere and at any time of the year. I hope that by the end of today's lecture, I will convince you that we have a method to do just that. So let me just introduce this topic by way of sharing with you some of the important molecules that are part of the challenges facing our planet. Our planet is facing issues dealing with clean energy, clean air, and of course, clean water. So hydrogen is a small molecule that when burned only produces water as a byproduct. So it's a highly desirable molecule that we need to figure out how to store. Carbon dioxide, let's say a child born today is breathing almost double the amount of carbon dioxide than a child born before the Industrial Revolution. So carbon dioxide in the atmosphere is a problem, and we need to find a way to pluck out carbon dioxide. And I suspect that would be the subject of the next talk you'll hear from Professor Jeff Freimer using metal organic frameworks. The third is water. And water, of course, is essential to life, but it is one of the most precious materials, and increasingly we are in need of water in arid regions and clean water, even in places where there is plenty of water. So let me just say that in order to address these vexing issues on clean energy, clean air, and clean water, we need to think about what kind of materials do we need to invent or work with in order to address these challenges. But I like to start by looking back and thinking about what are the materials that have been invented before and are being used today to address the problems that have emerged in the last century and will emerge in this century. So I guess let's make a mental list of the most important materials that are in use today. I think you and I will probably agree that wood is a very important material. Concrete, metals, glass, silicon, petroleum, plastics, pharmaceuticals, fabric, and paper. I would say these materials really are the most important materials today, and without them we would not have fast communication, we wouldn't be able to fly planes and so on and so forth. So they have impacted all aspects of our society. However, I believe that the next generation materials to address the problems that I have been talking about in terms of clean air, clean energy, and clean water have to be different. Okay, and these materials have to be able to carry out a way to store those gases and transform them into clean fuels, such as CO2 conversion to clean fuel, or trap water, as the subject of this presentation will be, trap water from air to deliver clean water. So I would like to propose that, in fact, metal organic frameworks have the scope, depth, and diversity to fill the materials gap that we are facing in addressing those topics. So metal organic frameworks, let me just describe what they are. They are made from metal units, shown here in blue, and organic units, shown in gray. We also have covalent organic frameworks. They look like this except without the metal. Now, the reason I make the point that these are really the materials of the 21st century, and that they are the materials that will address those problems, is because of the great variety that could be made. So for example, in this structure that I just showed rotating, all the components can be varied. They can be changed, they can be functionalized to alter the pore environment and tailor the pore environment for very specific molecular binding, whether it's hydrogen, CO2, or water. And they can be expanded to even incorporate much larger molecules. So there's a lot of flexibility built into the chemistry that we have developed since the mid-1990s. So we call this chemistry reticular chemistry. And in just simply stated, is that it uses the component of minerals and organics, combine them together to make new porous materials, as you see here. So this is truly infinite chemistry. In the history of humankind, there has not been a class of materials as extensive and as diverse as MOFs, or metal organic frameworks. So it's infinite chemistry leading to infinite materials and infinite applications. Now, a typical MOF, just like the one I just showed you, has an extremely high surface area, meaning that if I was to unravel a gram of MOF, it would cover an entire football field on the atomic molecular level. And it's that space that is available to trap molecules like hydrogen, carbon dioxide, and water. Okay, so in specific terms, a gram of MOF can have a surface area of 10,000 meters square per gram. And that has created tremendous excitement, because with the ability to functionalize the MOF interior, and tailor that pore for a specific function, then the possibilities are endless in terms of storing gases such as hydrogen that are difficult to store under practical conditions. But with MOFs, we are just a step closer to doing that. The same thing applies for CO2, to tailor the pores so that you can pluck out CO2 from the atmosphere. And indeed for water, to pluck out water from the atmosphere and concentrate it into the pores so that you can harvest clean drinking water. Well, you can imagine the excitement in the world about these discoveries. Back in 1995, where I started in Arizona State University, we made the very first MOFs and showed that they have permanent porosity, and they can be crystallized and characterized fully. And that really launched the field. Today, the field has grown to encompass laboratories in over 100 countries around the world. So it has become a global activity. And this new field that we've created, that I call reticular chemistry, pertains to linking molecules together to make extended structures, robust structures, just like the material that I showed you rotating on the screen a few slides ago. So with this ability to design materials on the atomic molecular level, and with the incredible porosity that these materials have, we can begin to address a formidable challenge such as the water stress in the world. This is a map of the aridity map, let's call it, of the world. And you can see all the regions that are not yellow are water stressed. And in fact, 1/3 of the world population lives in water stressed regions. And even in the regions where there is plenty of water, there are questions pertaining to water purity. So, and I think another thing to keep in mind is that almost 160 countries around the world import their water. So for many countries, this is also a national security problem. So our idea is that perhaps we could use the MOFs to address this stress, this water stress, because the current solutions, which already deployed successfully, such as desalination, they're great in providing water, but they also have tremendous environmental impacts, such as increasing the salinity of water and tremendous energy costs. Okay, there are desalination plants being built in the Middle East for production of 1 million cubic meters of water daily. But the impact on the salinity of water around those plants is tremendous, and it's not easily reversed. The other problem that we are facing around the world, not just in the Middle East, but in other parts of the world, is that including the US, Midwest, and even west of the US, is that the underground water is being depleted at a much higher rate than it's being replenished. So that's another part of the water stress. Even in some countries, as you see here in Sao Paulo, a dam is drying up, and the UN predicts that by the year 2050, almost half of the world population, or excuse me, even 5 billion people, not more than half, 5 billion people around the world will be facing the water stress problem. So I think that there is potentially a solution. And this solution is harvesting water from air. This is how much water is in the air at any one time. 3 sextillion liters of water exist in the air at any one time. This is a natural resource that if we can find a way of trapping this water in the air, we would be able to use it and recycle it back into the air. And it's a completely recyclable resource. We are not destroying water, we are just using it, and it is released back into the atmosphere. So the idea of harvesting water from air is not a new one. In fact, in many regions where there is a humidity in the air, high humidity, even natural species can harvest water. This beetle in Namibia, right off the in the coast there, as there is fog, it can harvest the water granules on its back where there is nano ridges that nucleate the water and build up the water droplet, which then, as you see here, seeps down to hydrate the beetle. So that's from fog regions. In other fog regions of the world, there are these devices that trap fog, just like sometimes you see on your window screen, to trap fog and collect water. Again, this requires high humidity. Also, what requires high humidity are these machines that are sold everywhere in the world for harvesting water from air. They work on direct cooling, where the water in the atmosphere is cooled down and therefore condensed and then collected. Now, the problem with these machines is that they work only on humidities greater than 60%. So at the humidities lower than that, they don't work. And if they do, it's only for a limited part of the year. So these are not solutions that work in the red regions of the world. You can see here that the direct cooling mechanism will not be able to accomplish water harvesting from air in these red regions, exactly where you want water harvesting from air. These will not work because they can only work at high humidity. So there are no solutions right now to trapping water from air in an energy economic way.